Okay, we were discussing the radix to FFT algorithm. We have discussed one algorithm which is called as decimation in time. Okay, so we have seen that when you compute the endpoint DFT, the endpoint DFT is basically computed using 2n by 2 point DFT using the two equations. The second part is xk plus n by 2 is equal to okay. This is what we have discussed in the previous class, and then we have drawn a structure that how you can basically get n by n point EFT from n by 2 point EFTs. Okay, so if you have to compute the 4 point EFT or 8 point EFT, we have taken example in this case. So you first decompose n as 2 into n by 2. So in the case of 8 point EFT, it is 2 into 4. So you divide this input sequence into two parts. One is the even samples 0, 2, 4, 6, and the second one is the odd samples x1, x3, x5, x7. Okay, and then if you know the 4-point EFT of this sequence and the 4-point EFT of this sequence, you can combine them to get a 8-point EFT. Okay, so if you know the 4-point EFT, you can combine these 4-point EFTs to get 8-point EFT. Okay, and then to find this 4-point EFT, we further divided this sequence into two parts. Again into, now this is the original sequence, you can see that, and if you divide it to even and odd samples, even the even sample you'll get x0 and x4. In the odd samples you'll get x2 and x6. And similarly here you'll get x1 and x5, then x3 and x7, and then you find its 2-point EFT. Okay, 2-point EFT of this, then you combine these 2-point EFTs to get a 4-point EFT. That will be the 4-point EFT of basically this sequence. Similarly, you find the 2-point EFT of this, 2-point EFT of this, combine them to get a 4-point EFT. That will be the 4-point EFT of this sequence. And then you finally combine the 4-point EFT of this sequence and the 4-point EFT of this sequence to get 8-point EFT, which will be the 8-point EFT of this sequence x0, x1, x2 up to x7. So your final answer will be in the same sequence x0, x1, x2 up to x7. But the inputs you are basically decimating in time. Okay, this is why it is called decimation in time algorithm. Decimation means you are basically, it is a terminology which is used in multi-rate signal processing when you reduce the sampling rate. So you reduce the half sampling rate is reduced to half because you discard half of the samples, so you decimate by 2. Okay, this is what was the algorithm, and I will draw the final structure at once so that it becomes clear to you. To get 8-point DFT, 8-point radix to decimation in time FFT algorithm. What is the flow chart for this? Okay, so you have 2-point DFTs. So 2-point DFT, the input to this is x0, x4, x2, x6. Similarly, x1, x5, x3 and x7. And then we have multiplied this with w at the power 0, okay, then add it with this, you'll get one sample, multiply with -1 and add with this, you'll get the next sample. This is 2-point EFT. Similarly, add with this, multiply with -1, add with this, you'll get the next 2-point EFT. Okay, again multiply, add with the top branch, -1, add here, another 2-point EFT. Add with this, multiply with -1, add here, you will get another 2-point EFTs. So we have first computed 4 2-point EFTs using this structure. Okay, now these 2-point EFTs have to be combined to get 4-point EFT, and similarly you have to combine then other 2-point EFTs to get the 4-point EFT. This is one 2-point EFT, this is another 2-point EFT. Now you have to combine them to get 4-point EFT. Okay, so how we have done that? We have multiplied this with w at the power 0, this branch, and w at the power 2. Okay, then added this with this and this with this, you get these 2 points. Then multiplied with -1, add here, add this with this, you get the next 4 points, next 2 points. This is 4-point EFT from 2-point EFTs. And similarly here you will get w at the power 0, w at the power 2, add with this, then multiply this with -1, add here, you'll get the next 4-point EFT. Okay, so this is now one 4-point EFT, this is another 4-point EFT. Now you have to finally combine them to get a 8-point EFT. Okay, so to get this 8-point EFT, now you have to combine these 4-point EFTs. And how you do that? We multiply this with w at the power 0, w at the power 1, w at the power 2, w at the power 3, and then add with the upper branches. Okay, and then multiply with -1, -1, -1, -1, and add this with this, this with this, you'll get the next 4 points. Okay, this is how you get the DFT. So your output is in the same order. You will get this as x0, this will be x1, x2, 3, 4, 5, x6 and x7. So this is the flowchart of radix to decimation in time FFT algorithm. So you have to keep in mind that the input that you must apply to this flowchart, it is not in the sequence, it is in basically the different order. You have to x0 you have to apply to this branch, x4 you have to apply here, x2 here, and x6 here. Similarly 1, 5, 3 and 7, and then you have to go in step by step. You have to find first the 2-point EFTs, then by combining the 2-point EFTs you find 4-point EFT, then by combining the 2 4-point EFTs you get a 8-point EFT. So the butterfly diagram for this structure is A, B, you multiply the lower branch with some phase factor, you get w under the power r into b, then you multiply this with -1 and add with the top branch, you get a minus w under the power r into b. Okay, This is called as butterfly. Now if you look at the computational complexity of this algorithm, you will again calculate how many multiplications and additions are required to compute n point DFT. Okay, so you will first see that in one butterfly how many multiplications and additions are used in a single butterfly. Okay, number of multiplications in a single butterfly is 1, and number of additions in a single butterfly is 2, because see your b is multiplied with double n to the power r only once. Okay, only one multiplication. Addition is 2, one is plus, and this minus I have also taken into addition, so plus here and minus here, 2 additions. So in one butterfly, so in a single butterfly you have one multiplication and one additions. So you simply compute how many butterflies are used in this entire structure. Okay, so first we see that how many stages are there. If you see 8 point DFT, if you compute, you have 3 stages. This is the one stage, then another stage, another stage. You have compute 2 point DFTs, then 4 point, then 8 point DFTs. Okay, so the number of stages that you have, it is basically log n to the base 2. For n, when n is 8, it is 3. Okay, and in each stage how many butterflies are there? In the first stage you see that there are 4 butterflies, 1 2 3 and 4. In the second stage again you have 4 butterflies. Okay, 2 butterflies here and 2 butterflies here. In the third stage again you have 4 butterflies. It means the number of butterflies that you have, number of butterflies per stage, that is n by 2 in general. Okay, so total number of butterflies, how many total number? It will be nothing but n by 2 log n, because log n is the number of stages, and in each stage you have n by 2 butterflies. So total number of butterflies that you are using in the entire structure is n by 2 log n. Now in one butterfly you need one multiplication and 2 additions. So total number of additions in radix 2 FFT algorithm is n by 2 log n, because it is multiplied with 1. And total number of total number of multiplications, this is total number of multiplications is n by 2 log n, and additions will be total number of butterflies is n by 2 log n. So in one butterfly you need 2 additions, so multiplied with 2, so this 2 will get cancelled, you will get n log n. This is the number of additions. Okay, so this is the computational complexity of radix 2 FFT algorithm. And if you compare it with the direct computation, in the direct computation how many multiplications you have? N square multiplications. In this case you have only n log n multiplications. So if you compare it, if n is 8, if your n is 8, you compute 8 point DFT. So using your direct computation and using your radix 2 FFT, how many multiplications will be used? In direct computation it is n square, that is 64. In radix 2 algorithm, now the number of multiplications is n log n. So n is 8 into log of 8, that is 3. We have only 24. Okay, so this is addition. If multiplication is n by 2 log n, so it is 4 into 3, 12, isn't it? If you use a, So for this is for n is equal to 8. If you use 16-point DFT, so in this case you have 256 multiplications, 16 square. But in this case it is simply what? N by 2, that is 8, into log of 16, that is 4, 32 only. So you can see by what factor you are reducing the number of multiplications and additions. Okay, so that is why this algorithm, it is computationally more efficient as compared to the direct computation of DFT, because the number of multiplications and additions that are required to compute the DFT is reduced. And this is basically how the speed is improved, because anyway, when you implement this algorithm on your DSP processor, the speed will depend upon how many operations are required. Okay, and for each operation you need some clock cycles to complete. So the less number of clock cycles it requires, the minimum is the time required to compute that algorithm. Okay, so it is very fast and efficient algorithm for computing the DFT. In fact, FFT has brought a great, you can say, revolution in the area of signal processing. Okay, so this is I will give a question for you. You have to compute, the question is that compute the 8-point DFT of a sequence xn, which is given by 1 1 1 1 1 1 using radix 2 decimation in time FFT algorithm. Okay, so I have given you only 6 samples, but you have to compute the 8-point DFT. Okay, or in between you can change some values. Suppose this is 4, this is suppose 2. Okay, so you have to first, what you have to do, you have to use 0 padding. So you have to use 2 zeros after this, 0 and 0, so that becomes 8. And then you have to apply this input to this structure here. Okay, so you give x0, then x4. x0 is your 1, so x0 will be here 1. Then you have to say x4. This is x0, 1 2 3 4. X4 is my 2. Then x2 I have to say 0 1. X2 is 4. And x6, 0 1 2 3 4 5 6. X6 is 0. Similarly, you can feed x1, x5, x3, x7. And then you have to first calculate w at the power 0. It is simply 1. So in the first part, when you get the output, it is simply addition and subtraction. So this output will be what? 2 plus 1, it is 3. This is 1 minus 2, it is minus 1. Similarly, here it is 0 plus 4, this is 4. And this is 0 minus 4, it is minus 4. Similarly, you can compute here. So this is 2-point DFT. This is one 2-point DFT. Then you have to combine them to get 4, then 4 combined to get 8-point DFT. So you have to find the final answer. What should be the answer for this? Okay. So next we will discuss radix to decimation and frequency algorithm, which is very similar to this decimation in time algorithm.